Hi y'all, welcome to Book 3, Proposition 35. To start, we're going to read the enunciation and then we'll get right in it. So, if in a circle two straight lines cut one another, the rectangle contained by the segments of the one is equal to the rectangle contained by the segments of the other. So, I've already done our givens. They're in red, but we're given circle A, B, C, D. And we're given that lines AC and BD cut each other at point E. And we're trying to prove that the rectangle contained by AE and EC equals the rectangle contained by sides DE and EB. And there's two circles on here because we're going to prove it two different ways. The first way that we're going to prove it is that point E is the center of the circle. And the second way we're going to prove it is point E is not the center of the circle. So, first thing we're going to do, the first circle does not need any construction, so we just get to hop on into the proof. So we're just going to restate that point E is the center to help us remember, and that's given to us. And then, for our second step, we're going to say that A, E equals E, C, which equals E, B, which equals E, D. And we know this because of book 1, definition 15, which is the definition of a circle. And so since all of these come out from the center, they're all equal. For our third step, we're going to use book 2, definition 1, which says that a rectangle is contained by the sides that make it up. And then we're also going to use statement 2, and I'll kind of explain that as we go. So the rectangle contained by sides AE and EC, so these are the sides that make it up, equals the rectangle contained by sides DE and EB. And we know they equal each other because in statement 2 we said all of these lines are equal, so no matter how we flip this, they'll all be the same. They'll all be the same rectangle. And so that's it for the first circle, that's it. That's all we have to do for the proof. And so for our second circle, we're gonna move on, and so now point E is not the center. So now we're gonna need a center. So the second circle does require a construction, and this is where it starts, with finding the center of the circle. Book 3, Proposition 1 helps us with that. Book 3, Proposition 1 says that you can find the center of the circle. And our center is going to be point F. So let's draw that on here. So there is the center of our circle. The next thing that we're going to do is we're going to drop some perpendicular lines. So we're going to have FG, which is perpendicular to AC, and then we're going to have FH is perpendicular to DB. And this is because of book 1, Proposition 12 allows us to drop from a certain point. We can drop perpendicular lines onto another line. So here's our point, and we're going to drop perpendiculars to both sides. So I'm going to grab my ruler. I'm going to do that super fast. There they are. This is G and H. Now, we're going to connect lines. We're going to connect the points F and B to make line F, B, and we're going to make line F, E, and we're going to make line F, C. And we can do this because of postulate 1. Postulate 1 says that you can connect dots to make a line. And there is a fancy song. I'm not going to sing it because nobody wants to hear me sing. But if you want to sing it at your house, be my guest. So, there's FC. I'm using a ruler to keep my lines straight because I like pretty straight lines, but you don't have to. And then there's FE. And lastly, FB. So, this concludes our construction, and just so you can see where that is, I'm going to put a bracket around it. So that was our construction. And now we can get on into the proof. So the first thing that we're going to do is we're going to say that FG bisects AC. So if you don't know what bisect means, it basically means that it gets cut in half. So it'll be that now AG equals AC. They're equal to each other. And that is because of book 3, proposition 3. Book 3 says that if in a circle, if a line drawn from the center, point F, to another line is cut at right angles, which we know it's cut at right angles because here we made it a perpendicular line, it bisects that line. So it is now bisected. They equal each other. And so then the next thing that we're going to do is we're going to use book 2, proposition 5, which is quite a doozy, so I'm going to write it out and then I'll explain it. So it's going to be the rectangle contained by lines A, E, and E, C, plus E, G squared equals GC squared. So book 2, proposition 5 says that if you have a line cut at equal and unequal parts, which we do, it's cut at equal parts here and unequal parts here, that the rectangle contained by the unequal segments, so AE and EC, plus the square on the points of intersection, G and E are the points of intersection, so the square on that line is equal to the square on the half. So the half is GC because it's half of AC. And then the next thing that we're going to do is we're going to use common notion 2 and 4 to add GF squared to both sides. So we're going to have AE, the rectangle contained by lines AE and EC plus EG squared plus GF squared, which is what we're adding, equals GC squared plus GF squared. And combination 2 says that if you have equals, which we did, and you add equals to that, which we did, GF equals GF because of combination 4, the sums will be equal. And so now our sums are equal. If you don't know, combination 4 says that things which coincide are equal to each other. So GF equals GF. And then the next thing that we're going to do is we're going to pull out some triangles. We're going to pull out a triangle. I'll move so you can see in a second, but we're going to pull out this triangle and this triangle. So this is triangle FGC, and this little triangle here is FGE. So these are the triangles we're doing, and we're going to use book 1, proposition 47, which is the Pythagorean theorem. And so we're going to do a squared plus b squared equals c squared. That's what the Pythagorean theorem is, or proposition 47. So we have fe squared equals gf squared plus ge squared, and then we have that fc squared equals fg squared plus gc squared. So these are the two triangles that we pulled out. They're here and here, and we use the Pythagorean theorem. And so now we're going to use common notion 1, which says that things which are equal to the same thing are also equal to each other, which we just always, my class always says equals, 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 which can be confusing, but that is the true definition. And then, so this allows us to plug fe and fc into this part of the equation and like this part of the line. So now we have the rectangle contained by lines AE and EC, plus we're going to put FE in and FE squared instead of the other stuff, equals, and we're going to put FC squared in for this last part. Yay! All right. The next thing that we're going to do, we are almost there, ladies and gentlemen. You might be able to see it in the next few steps, what we're going to be doing. So now we're going to say that FC equals FB. And that's because of book 1, definition 15, which we talked about earlier, is a definition of a circle. And so these lines are equal because they're both from the center. And now we are going to get to use common notion 1, equals, 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 again, to plug FB in here. So now we have the rectangle contained by lines AE and EC plus FE squared equals now FB squared. And now we get to do a fun little trick. So I'm going to write it and then explain it. So it's going to be the rectangle contained by lines DE and EB. And if you are wondering where this part of the proof was, here it is. It's coming in now. Plus the square FE equals FB squared. Now, this is true because of statements 8 through 14. You can also say similarly, whichever you prefer. But we just say that because this is true because of all of these same reasons, but we don't want to write them out again. So we just say statements 8 through 14 or similarly. And now we're going to use common notion 1 to add them all together. The this is going to be really long. So we have the rectangle contained by lines A, E, and EC plus the square FE equals the rectangle contained by lines DE and EB plus FE squared. So now for our last and final step, we're going to use combination 3 and 4. Again, in the same way that we used 2, but they're like the opposite. The same way we used 4, things that coincide are equal to each other. We're going to say that FE squared equals FE squared because they're the same thing. And then combination 3 says that if you have equals and you subtract equals, the remainders will be equal. So we're going to take out this FE squared. And we are left with the rectangle contained by lines AE and EC equals the rectangle contained by lines DE and EB. And congratulations, you're done. You've proved it both ways with E as the center and E not the center. So now we get to write the best letters ever. Q, E, D. You're done.